This research was initiated and instigated and also funded by nornnorn, which is the world's first circular economy product subscription startup. And the primary product that they've started with on a subscription is mattresses. Other parts of mattresses are relatively simpler to recycle. The polyurethane foam, which is the spongy part of the mattress, is the hardest part. It's not cheap nor easy to recycle, and it's difficult to make it economically viable. In figuring out a way to recycle the foam, they had several criteria. It needed to be an eco-friendly and sustainable way. It also needs to be a way that enhances the value of the mattresses. So for the next two presentations, we're going to discuss these topics. The first presenter, we would like to invite Dr. Tanujjal Bora back onto the stage to present the results of the foam upcycling tech, nanotechnology-based polyurethane upcycling project.
Thank you very much. So, can I have a slide, please? Okay. Okay, thank you very much for the brief about the background. So the presentation that I'm going to give is basically it's just an overview of what we are doing in the last few years and some of the key outcomes of this project. Okay? So before I start, I want to inform that the project is supported by Royal Academy of Engineering UK, NSTDA Thailand, the PMUC and Ministry of Higher Education Thailand, and also our private sector partner nornnorn or Circularity. Now, first I'm going to tell you about what is polyurethane, because you are hearing about it, but some of you may not be familiar about some of the technical details of polyurethane. Now, when we say plastic, it's a very broad family, but among that there are two basically categories of plastic. You have thermoplast and thermoset. So thermoplastic is the plastic that you can use and then you can recycle very easily. You can remold, you can make something else out of it, then you can resell it, and then again collect it, remold it, resell it. So those are thermoplast type of plastic. But polyurethane is unfortunately is a thermoset type of plastic, which is basically it becomes hard when you heat it, but then you cannot remold it. That means next time if you want to heat it again or you want to do something with it, it basically disintegrates molecularly and it releases different kind of byproducts. Some of them can be toxic. So what happens is the traditional ways of recycling methods that are available today are not applicable to this type of plastic. So that's the biggest challenge, right? So and where is polyurethane? It's almost everywhere nowadays. You can look into these pictures. You will find it in the automobiles, in our house, shoes, mattresses, furnitures, everywhere. Okay? So therefore, if we specifically look at this flexible polyurethane, so basically all polyurethane is same. It's just their mechanical form. Some of them are rigid, some of them are flexible based on the requirement. Okay? So when you need comfort, we use the flexible polyurethane. Okay? But anyway, these polyurethane, which are typically the flexible polyurethane, they are everywhere and their market is growing gradually. Okay? And if you look at these statistics, flexible foams are one of the dominant category of polyurethane that we use in our day-to-day life. And Asia is the biggest consumer, okay, for this type of plastic. So therefore, obviously, we are, that means producing a lot of waste at the end, right? So, but the question is then, what do we do with this waste? Because we cannot remold or reuse it or make something out of it. So unfortunately, what happens is this waste that we see, it either goes to landfill or some part is generally it's burned, so which is also not eco-friendly. Because the problem is you cannot do anything with this plastic once it becomes waste or once it reaches to the end of the product life. Okay? So for example, the mattress in our case, we can dismantle it, the textile we can recycle, the metal springs inside can be recycled, can be reused for further manufacturing of the mattresses. But the foam, what to do? Nobody has this answer, right? So this is what basically NAPS, he came to us in 2018 with this problem, because they want to change it. And they want to see whether it is possible to do something with this waste. Can we convert it in a more sustainable and more eco-friendly way and bring some value to this waste? Okay? And we started then thinking about it, what can be done. But we started looking into like, okay, let's see what is the existing technology available. Right? So fortunately, there are certain methods available to deal with this type of plastic. Some of them are mechanical processes, some of them are chemical processes, some of them are thermal or thermochemical processes. But again, each of them, it's there in literature, you will find it, but you will not see them practically somebody doing it or implementing it. The reason is some of them are not eco-friendly probably, some of them probably are very, very expensive, not practical. Some of them doesn't have a very large market, so it means not very attractive, right? So end of the day, nobody is getting encouraged to use some of these techniques. So while looking into it, we fortunately identified a particular chemical approach, which is called acidolysis. It is basically a process in which we use acids to break down the polyurethane molecules, okay, into two fragments. So this is a typical structure of the polyurethane molecule that you can see here. So don't worry about the chemical structure. But what we do is we add a certain type of acid to it. Okay, we let them react, and the final product is it gives you two fragments. One is called polyol. Okay, so this one, and then there is a hard segment with it. Now the benefit of this process is that this particular component that you get, the polyol, is actually the raw material that you need to make polyurethane. Right? So that means there is a way to reverse engineer this material and go back to the origin. Right? Of course, the process takes quite a lot of energy. It happens up almost about 200 degrees Celsius, right? So that means it's again not very, very maybe sustainable or maybe not very economical. So then we started thinking, okay, we have a possible candidate here, right? But then can we make this process a little bit better, a little bit more sustainable? Can we reduce the energy that we are using to break down the molecule, right? So that's how the idea came. Okay, so you see this slide, you see the rice, but we cannot eat the rice when it is raw because our digestive system will not process it properly. Right? So what we have to do it, we have to cook it. After that, no problem with the digestive system. Right? So it means if you make the rice softer, the process becomes more efficient. So that's how we came up with the idea, and we discussed, and finally we reached, and we started this project. That the idea is, can we make this material softer before we actually do the acidolysis or the traditional methods we apply? Okay. And that's how we came up with this project, where we proposed, okay, let's do it this way. We take a two-step approach. The first step, we change the mechanical form of the waste, and we make it a little bit softer. And then step 2, we use the traditional method, which is already there. We don't have to break our head in that. Okay? There is no need to reinvent the wheel. Right? So with that, we came up with this concept is that, okay, we have the polyurethane foam that goes to the product, and at the end of the life, we get the waste. Now comes our approach where we do the reverse engineering to get this polyol from this waste. And that can be fed back to the manufacturer, which can again use this recycled polyol to make the foam again. So it's a completely circular approach in a way like it is closing the loop. In this whole process, the ideal process, there is no waste formation. So the product goes to waste, waste goes to the raw material goes back to the product again. Okay. Of course, the challenges are that how do we do this in a more sustainable way, and more importantly, at the end, this should be profitable. Profitable in a sense, both financially as well as from the environmental point of view. Okay. So next few slides, I will briefly show you just a few outcomes, which are the outcomes of our project. But before that, these are the 3 main goals that we have for the project. The first is, of course, to develop this hybrid circular approach to deal with these polyurethane foam-based waste. The second goal is to develop a sustainable business innovation model. Okay, to look into, okay, if we develop this technology, how do we convert it to a sustainable business? Because end of the day, we want somebody to take it and commercialize it. Okay. And then the goal 3 is to develop a new knowledge, transfer the knowledge, and disseminate. So that's why we are here today. So that's a part of the goal 3. Now goal 2, my colleague Dr. Park will explain. So I will mostly focus in goal 1. So this is the step 1 what we did. I will cut short the story. It's a 5-year long story, but end of the day what we have is we use some nanotechnology-based approach where we have developed some catalyst which are extremely small. So how small is basically they are 10,000 times smaller than our hair. So it's so small that you cannot see it, you cannot touch or feel it. So it's like an invisible material, but we use this material to do something with the foam. So what we do is we take the material, that means our catalyst particles, these are electron microscope images, so that's how we see them actually. And then we need other inputs. The one input is the foam, of course, that means the foam that we want to convert, and then we need some light. Okay, so these catalysts, they are designed in such a way that they work under certain type of light. So we can tune them. You can make it like work under a particular type of light, say for example ultraviolet light, or you can tune them to work using simply the light from the sun that we get. Okay, so that means you can tune the catalyst material to make it a completely solar-based process. Okay, you don't need to spend electricity to do this process. Okay? It can be completely renewable. And how do we know that our process is working? Means our goal in the first step is to make the material softer. Right? So this is a DSC data you can see here. Okay, the red graph that you see, it indicates the enthalpy of melting point. So basically, if you see here, it is about 335 degrees Celsius. So that's where polyurethane will start to melt. Now, after we treat this foam with our catalyst material, you see that temperature goes down from 335 to 320. So that is an indication that now you need less energy to break down the material. So this tells us that yes, there is something happening to the material and it is partially now degraded. Molecularly there is a change. So we then feed this degraded material, which are partially degraded of course, to step 2. In that we follow the traditional acidolysis process. Okay. So here you can see in this diagram the surfaces. So after the treatment, you see this foam surface, you can see so many ruptures and cracks and holes. Okay, so that's the visualization of the partial degradation of the foam. Okay. Now once we do that, we follow the traditional method of acidolysis, but the difference now is we can do the same process at 140 degrees Celsius. Okay, that means almost 30% drop in terms of the energy that is required to do the acidolysis. Okay, so now what we have is, that means the process does not require the energy that it used to take when there was no, that step 1 was missing. However, at the same time, we started looking into the acidolysis process, and we started thinking, okay, so still we require this energy, 140 degrees Celsius. So from where this energy comes? So of course we have to use some kind of heater to heat the system, or there has to be some heat source from where we get the heat, right? That means still we have to use some electricity for that. Okay? But the good thing is, since the temperature is much less now, 140, right? So this is a temperature that we can also achieve by using simply solar heaters. So that means there is still a scope that you can make this entire process completely electricity free. Okay? And that is where is a big change from energy perspective, from emission perspective. Right? So overall, if you see, what does it mean? That after we develop this 2-step process, what we have is we have a waste-free circular upcycling process for our polyurethane foam. Okay? It is helping us to reduce the amount of raw material dependency to make polyurethane. Okay? And it's a low energy eco-friendly approach. Okay? So when I say eco-friendly, that means the waste which we are generating today, the 100% of this waste can be converted back to polyurethane. So the yield of this, or the conversion yield of this process is 100%. That means doesn't matter if it is 100 kgs, 1000 kgs, 10,000 kgs of waste, all waste can be converted and we can get the polyol, the component that we want. Okay? So that's why it is, we call it waste free. At the end, there is no waste left. Low energy, we have approximately reduction in terms of the energy is 30%. That means that is only considering the electricity that we are using. And if you do some calculation, that is roughly 350 gram of CO2 reduction per kg of the waste that we get, if we follow the approach that we have developed. Okay? And that's a very, very big change, because it is, when we are talking about the actual scale of the waste that we generate, it is in thousands, hundreds and thousands of kgs. Okay? So therefore, there's a big change in terms of the carbon emission to the atmosphere. Plus, the approach is unique. Okay? And it can give you some unique business ideas. So it will also help the local entrepreneurs to come up with something innovative, right? And of course, at the end, it is profitable. And that is very important, because that is how we can attract the private sectors to come forward. Okay? and take this technology and scale it up. Okay. Of course, at the same time, here is a statistics for the polyol, that the final product that we are making, right? So you can see the market size of polyol, it is growing. Okay. So there is a lot of business opportunities. And this opportunity now we can create from something, a polyurethane-based waste, which currently has nearly no value. Okay. So that's where the project is about. Of course, I skipped a lot of things because of the time limitation, but I highlighted some of the key findings at the moment. The project is still ongoing, and we are relatively at an early stage, but we see a lot of promise in it. Okay, so I'm here, or even in later, if you would like to contact, here is my contact details, my email and phone number. I'm very happy to answer your questions. And thank you very much for being here. And there are much more actually there results, so my colleagues will introduce and talk about those results in the following talks. Yeah. Thank you very much.
Thank you, Dr. Bora.